Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at Proton NMR Spectroscopy. We're going to talk about what Proton NMR Spectroscopy actually is, the theory behind NMR spectroscopy, and how chemical shift data can be used to help analyze organic compounds. The use of Tetramethylsilane, or TMS, as a standard is outlined and specific examples given. Peak splitting and spin-spin coupling, as well as carbon-13 NMR spectroscopy, have been outlined in separate videos. Check the links in the description below. Proton NMR spectroscopy is a technique used to analyze hydrogen-containing compounds in organic chemistry. It enables the number of unique hydrogen or proton environments in a molecule to be determined, and information about possible groups bonded to these hydrogen environments can be predicted, giving useful clues about the structure of a compound. The N, M, and R stand for nuclear magnetic resonance. Hopefully, why those words are used will become a little bit clearer as the video goes on. In a molecule, a hydrogen or proton environment refers to a hydrogen atom and the bond that it has to another atom or group. A unique hydrogen or proton environment is where a hydrogen atom is bonded to different atoms or groups compared to another hydrogen atom in the same molecule. This can sometimes be tricky to see, as even if two hydrogen atoms are bonded to the same types of atom, if those atoms themselves are bonded to different atoms or groups to one another, then they are in different or unique environments. For example, in the molecule ethane, there are 6 hydrogen atoms and therefore 6 hydrogen or proton environments. However, there is only one unique hydrogen environment here, as all 6 hydrogen atoms are bonded to the exact same atoms and groups. A carbon atom bonded to 2 other hydrogen atoms and a CH3 group. Whereas, if we have a look at ethanol, there are still 6 hydrogen atoms and therefore 6 hydrogen environments, but this time there are 3 unique hydrogen environments. The first is the hydrogen bonded to the oxygen in the OH group. The second is the 2 hydrogens bonded to the carbon bonded to the OH group. And the third is the 3 hydrogens bonded to the carbon at the end of the carbon chain, carbon-free. Be careful with this idea of unique hydrogen or proton environments. There can be more than one hydrogen in a unique environment. For example, there are 2 hydrogens here in the second environment and 3 in the third. If 2 or more hydrogen atoms are bonded to the exact same atoms and groups that are themselves bonded to the same atoms and groups, they are in the same environment. Central to Proton NMR spectroscopy is the nucleus of hydrogen atoms within a molecule. The nucleus of a hydrogen atom is just a single proton, and this is why we refer to Proton NMR spectroscopy and proton environments. Really, we're just talking about hydrogen atoms and their nuclei. As particles can rotate in 2 directions, they can have what are called 2 possible spin states. We call these spin up and spin down, often shown as positive half and negative half. As a result, the proton in a hydrogen atom can be either spin up or spin down. Now, in reality, spin isn't exactly like a particle rotating, but it's a nice way to think about it at this level. Now, when a charged particle or group of particles spins, it generates a weak magnetic field. If the nucleus of an atom has no overall spin, then it won't generate a magnetic field. However, if it does have an overall spin, like the proton in the middle of a hydrogen atom, then it will have a weak magnetic field around it as it spins on its axis. It kind of wobbles a little bit in the process. Hopefully you can remember from early physics lessons that magnetic fields have a direction based on north and south, meaning a spinning proton acts a little bit like a bar magnet, with a very small north and south pole. The magnetic field direction a spinning proton has is based on its spin. Change the direction of the spin and the direction of the magnetic field around the proton will also change, a bit like flipping a bar magnet upside down. If an organic substance that contains hydrogen atoms is placed in a large external magnetic field, the spin of all the hydrogen nuclei, protons, will align themselves with this magnetic field and as a result become slightly lower in energy and more stable. Essentially, one spin direction becomes lower energy, the one that's aligned to the external magnetic field, and the other direction becomes higher energy, the one that goes against the external magnetic field. The protons will all exist in the lowest energy state possible, meaning they will all have the same spin with the lowest energy. If a specific amount of energy is absorbed by these protons, however, their spins can be changed to the higher energy one, and as a result, they will have a magnetic field that is opposite in direction to the larger external magnetic field. This process is called resonance. This specific amount of energy can be given to the protons in the form of a radio wave. Only radio waves of a specific frequency will provide the exact energy needed to flip the proton spin. Radio waves that aren't the specific frequency won't be absorbed and will pass straight through the sample. A proton from a hydrogen atom in a different environment to another will need to absorb a slightly different amount of energy to resonate, and as a result, it will absorb a different frequency radio wave. By sending a range of radio wave frequencies through a sample and detecting those that pass through, we can determine which frequencies have been absorbed. The number of different frequencies absorbed will show how many different or unique hydrogen environments there are in the sample. It is actually the difference in frequencies absorbed that are important in Proton NMR spectroscopy, rather than the actual frequencies themselves. Because of this, a standard is used to enable absorptions of different frequencies to be compared for different proton environments within samples. The most common standard used is Tetramethylsilane, TMS. In TMS, there is only one unique hydrogen or proton environment, and all hydrogen atoms have a relatively high electron density around them. This is because the silicon atom bonded to the carbon atoms in TMS has a lower electronegativity than the carbon they're bonded to. As a result, electron density is actually high around the carbon atom, meaning electrons aren't pulled away from the hydrogen atoms bonded to the carbons, leaving a high electron density around the proton in their nucleus. This high electron density around the proton shields it from the external magnetic field and actually makes it slightly easier for the spin of the proton to be flipped by radio waves, meaning lower energy radio waves of a lower frequency are needed. In all other organic molecules, hydrogen atoms won't have such a high electron density around them, as it's rare for hydrogen to be bonded to atoms with a lower electronegativity than itself. As a result, the proton in a hydrogen atom usually has less shielding around it and experiences more of the external magnetic field in NMR. Slightly more energy is needed to flip its spin, meaning higher energy radio waves of a higher frequency are needed compared to the protons in hydrogen atoms in TMS. How frequencies of absorption for protons in a sample compare to the frequency absorbed by the protons in TMS is measured using something called chemical shift, ppm. The absorption for the resonance of protons in hydrogen atoms in TMS is given a chemical shift of 0, as in everything else is compared to this point. For example, there are two unique hydrogen environments in methanol. The hydrogen bonded to the oxygen atom has a low electron density, as oxygen has a higher electronegativity than the hydrogen, and as a result pulls electron density away from it. This means there is less shielding around the proton in the hydrogen atom, and it experiences a greater amount of the external magnetic field, making it harder to flip its spin. A higher frequency radio wave is needed, and this is said to be downfield of the reference and standard for the proton environment in TMS. The other hydrogen environment, the three hydrogens bonded to the carbon, have a higher electron density than the hydrogen bonded to the oxygen. As the oxygen has a high electronegativity and pulls electron density away from the carbon atom as well as that first hydrogen atom, the other hydrogens bonded to this carbon will also have electron density pulled away slightly as a result. This means that they too will have less shielding than the protons in TMS, and will have a chemical shift slightly downfield to the reference of TMS as a result. As they have a greater electron density than the hydrogen bonded to the oxygen, however, the chemical shift will be less than for the hydrogen proton in the OH group. When shown on a graph or spectra, we can easily see how the two absorptions for each hydrogen or proton environment in methanol compare to that of the hydrogen protons in TMS. It's important to make sure the solvent used in Proton NMR spectroscopy won't interfere with the spectra produced. To get around this, the solvent must be proton-free. Deuterated solvents such as CdCl3, deuterated trichloromethane, are used. Deuterated means contains deuterium. Deuterium, or heavy hydrogen, is an isotope of hydrogen that has a neutron in its nucleus as well as a proton. The nucleus contains two particles and as a result won't have an overall spin, as the spin of the proton and neutron will always be opposite, meaning they cancel each other out. As a result, these nuclei can't be made to resonate and won't show on an NMR spectra. Interestingly, for OH and NH bonds, the hydrogen atoms in the bond will swap and can be exchanged with deuterium atoms from D2O, heavy water, if the two get mixed together. When this happens, the deuterated hydrogen atom, now bonded to the oxygen or nitrogen in the molecule, will no longer show up on an NMR spectra. This means when a compound is mixed with D2O and then an NMR is rerun, if any peaks disappear, they must represent an OH or NH group. A really useful part of Proton NMR spectroscopy is that the ratio of areas under each peak are proportional to the number of hydrogens or protons in each environment. The ratio can't tell us the actual number of hydrogens in each environment, however, only the ratio between them all. For example, with propane, there are two unique hydrogen environments. The hydrogens bonded to the carbon in the CH3 groups are all in the same environment, as they are all bonded to a carbon atom that is bonded to a CH2-CH3 group. The two hydrogens on the second carbon, the CH2, are also in the same environment. This means there are 6 hydrogens in one environment and 2 in the other, a 3:1 ratio. This means the area under the peak in a spectra for the first environment will be 3 times bigger than the area under the peak in the spectra for the second environment. These ratios are sometimes shown on spectras as integration ratios. Using Proton NMR then, we can find out both the number of unique hydrogen environments in a molecule by the number of peaks on the spectra, and get useful information about how these environments may be arranged from the chemical shifts of each peak. Even in different molecules, hydrogen atoms bonded to the same groups often have similar chemical shifts. Data tables of these chemical shifts can be produced that enable spectra to be analysed quickly. For example, using the one shown, we can see hydrogen atoms single bonded to a carbon atom that is only bonded to other carbon atoms and alkyl groups will have shifts somewhere in the range of 0.7 to 1.2 ppm. And hydrogen atoms bonded to a carbon that is double bonded to an oxygen atom in an aldehyde, for example, will have shifts somewhere around 9 to 10 ppm. This kind of makes sense based on what we were looking at with electronegativities earlier. The more electronegative the element the hydrogen atom is bonded to, the less electron density there is around its proton, and the greater the chemical shift from the proton reference in TMS, as that proton had lots of electron density around it. For example, in propanol, there are 4 different unique hydrogen environments. In the first, the hydrogen is bonded to one oxygen atom. In the second, the hydrogen atoms are bonded to the carbon bonded to the OH group and the CH2CH3 group. In the third, 2 hydrogen atoms are bonded to a carbon atom that is bonded to a CH2 OH group and a CH3 group. And in the fourth, 3 hydrogen atoms are bonded to a carbon that is bonded to the rest of the molecule. We can predict where the peaks for each of these unique environments are likely to be on a spectra by thinking of electron density. In the first hydrogen environment, the high electronegativity of the oxygen atom will pull electrons away from the hydrogen atom's proton, meaning, as we've just seen, a greater ppm shift, far from the 0 ppm reference of the hydrogen atoms in the TMS standard. For the second environment, however, the high electronegativity of the oxygen atom will also pull electrons away from the carbon atom. That will itself then have to pull electron density away slightly from the hydrogens it is bonded to, meaning those hydrogens will also end up with a low electron density. As a result, they will also have a large ppm shift from the TMF reference. For the other 2 environments, the hydrogens are bonded to carbon atoms that are further from the oxygen, and as a result will have a slightly higher electron density around them, meaning less ppm shift. Technically, the hydrogen environment of the CH2 group hydrogens are closer to the oxygen in the molecule, meaning it has a slightly larger shift than the CH3 group hydrogen environment. As an extra note here, if we were to predict the spectra fully, we can think about the integration ratios for the areas under each peak. The ratio of hydrogen atoms in each environment is 1 to 2 to 2 to 3, meaning this is the same ratio we should see for the areas under each peak in the spectra. So, to summarize, Proton NMR spectroscopy is a technique used to analyze compounds in organic chemistry. Spectra are produced that give information about the number of unique hydrogen environments in a molecule, based on a number of peaks in the spectra, how these environments may be arranged, based on the chemical shifts of these peaks, and the ratio of the number of hydrogen atoms in each environment, based on the ratio of areas under each peak in a spectra. In Proton NMR, the nucleus of a hydrogen atom, a proton, has its magnetic field direction flipped against the direction of an externally applied magnetic field. The spin of the proton gets flipped in the process. Energy is needed to do this and comes from radio waves. Depending on the specific environment of a hydrogen atom, different amounts of energy are needed to flip the spin of its proton, meaning hydrogen atoms in different environments in a molecule absorb different frequencies of radio waves as their proton spin flips. The number of different frequencies of radio waves absorbed by a sample will be the same as the number of unique hydrogen environments in the molecule. It isn't the specific frequencies absorbed that are important, it's how they compare to each other, meaning a standard is used that all measurements are compared to. The common standard used is Tetramethylsilane, TMS. In TMS, there is only one unique hydrogen environment, and the protons of each hydrogen atom have a relatively high electron density around them. This high electron density shields the nucleus from the external magnetic field. In all other organic molecules, a proton in a hydrogen atom won't have such a high electron density around it, as it's rare for hydrogen to be bonded to atoms with a lower electronegativity than itself. As a result, such protons have less shielding around them and slightly more energy is needed to flip their spin, meaning higher energy radio waves of a higher frequency are needed. How much the frequency absorbed by a proton in a sample is different to the protons in the hydrogen environment in TMS is described in terms of chemical shift, ppm. Certain hydrogen atom environments have similar chemical shifts, and spectra can be analysed using data tables for chemical shift data. The less electron density there is around a hydrogen atom's proton, the greater the chemical shift. This is why hydrogen atoms bonded near oxygen in a molecule generally have greater chemical shifts than those further away, as oxygen has a high electronegativity and causes electron density to be pulled away from the hydrogen atom's proton. The area under each peak in a spectra is proportional to the number of hydrogens in each environment. This means the ratio of hydrogens in each environment can be determined from a spectra. When choosing a solvent to use for Proton NMR, it is important to make sure it won't interfere with the spectra. Deuterated hydrogen atoms are used in solvents such as deuterated trichloromethane, CDCl3. Deuterated hydrogen is an isotope of hydrogen that has one neutron and one proton in its nucleus, given an even number of particles and meaning the nucleus has no overall spin. As a result, it can't be made to resonate and won't show up in an NMR spectra. For OH and NH bonds in a sample, if D2O, heavy water, is added, the hydrogen atoms in those bonds will be swapped and exchanged with deuterium atoms from the D2O. When this happens, the deuterated hydrogen atom, now bonded to the oxygen or nitrogen in the molecule, will no longer show up on a spectra. This means when a compound is mixed with D2O and then an NMR rerun, if any peaks disappear, they must be due to the presence of an OH or NH group in the molecule. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.